All right, so we've gone through electrostatics, and you now understand the basis of electric charge and how that happens, how we build up charge, and we've also moved into a little bit how charge can move from one place to another. And that's a great setup for talking about the reason why we really care about electricity is electric current, electric power, and energy, because it's these topics that are going to help us understand how our cell phones get charged, how the TVs work, all the stuff that is important to our daily life. So let's go ahead and get into this. So first of all, electric current, the definition of current is the flow of electric charge by the movement of electrons. We know this. You understand, remember, when we look at these models, electrons are the only parts of the atom that move. We have these positive centers of the atom, and that represents the positive charge in the middle because we have protons in the nucleus. We have neutrons in the nucleus. The neutrons don't participate in the electrical process at all because they're neutral. Therefore, the nucleus of the atom is overall positive. But because of that strong nuclear force, remember, nothing in the nucleus is able to move. So the positives are there, the negatives, the electrons on the outside, move from one atom to another. And specifically, they're going to move from the negative side of a battery to the positive side of a battery. So as you can see here in this illustration, it's literally almost as if they're just kind of trading places from one atom to the next. This one will lose an electron, the next one will lose an electron, and they'll just kind of keep taking each other's place. That's kind of a little bit of a very, very simplified model of how electric current works. To go into it a little bit farther, imagine that we have some object or some area that has acquired a negative charge and another one that acquires a positive charge. We'll just say this is negative 10, positive 10. Arbitrary units for right now, unitless. And then if we connect these two with a conducting wire, with any kind of wire, electrons will flow spontaneously. And remember, that word spontaneously means automatically, naturally, just like the downhill flow of water. The electrons will spontaneously flow from negative to the positive. And this shouldn't be new to you because this is just conduction. We talked about the methods of charge transfer in the previous section on electrostatics. The first one was conduction, and the reason it was the first one we talked about is because that's the most common one. Conduction is the method of charge transfer that we use for basically all of all the electrical stuff that we use. Every bit of electrical devices that we have uses conduction by conducting materials, either aluminum or copper or some other kind of conducting material, usually metals. So the electrons spontaneously flow from negative to positive. Now, here's the beauty of this, and here's where science meets engineering. Turns out, if we put any device in the way of that electron flow so that the electrons are forced to flow through that device to get to the other side, now the electrons can do some work for us as they flow. In other words, they have energy from being on this negative side, and they can now use that energy to be converted into something else, like light energy in the case of this light bulb, or anything else. So the cool thing is if we force those electrons to go through the device we want them to go through, before they get to the other side, now the electrons are going to do work and they run the devices that we know and love. And that's why this is important. But there's a problem. The problem, as you might have suspected, is if electrons are flowing from negative to positive, that means electrons are being lost from this side, which means it's becoming more positive. And the electrons are being gained from this side, which means it's becoming more negative, which means the flow is eventually going to stop. That flow stops when the potential difference is zero. When the potential difference is zero. Now, you need to understand that we use the term potential here as in potential energy, electrical potential energy. Before the electrons started to flow, there was a lot more potential energy on this side than there was on this side. Therefore, there was a difference in potential energy. There was a difference in potential. And the word potential also means voltage as well. When those charges equal out, when the potential energy is the same on both sides, that means the difference in potential is zero. So the potential difference is zero, which means there's no more charge, which means the voltage is zero. So you need to understand now that the word potential difference also means voltage. Let me show you an example of this. So this is a really simple video that has a capacitor in it. I don't want to teach you about a capacitor, but the only thing you need to know about this capacitor is that it has been charged, and there is charge that is being held on these two terminals of the capacitor. This is the negative terminal, and this is the positive terminal. So right now the electrons are collected around this negative terminal inside the capacitor, and we have a light bulb right here. There's a wire leading from the negative terminal, and we're going to touch one side of the light bulb. The other side of the light bulb is connected by another wire around to the positive terminal. So this is similar to this picture that I just showed you a little while ago, where we have a positive and a negative. We have negative that flows spontaneously to the positive. But as I said, the flow stops when the potential difference is equal. Watch what happens. All right, so here's our capacitor. We're going to start the video. We connect it anytime now. And the light bulb does indeed light up. But if you watch the bulb, it dims over time, and the reason it's dimming is because as the electrons flow through this, they're simply flowing from the negative terminal through the light bulb back around to the positive terminal, and they're being redeposited on that positive terminal. And when the light bulb goes out, the potential energy of both sides is equal. In other words, there is no more negative and positive. The negative has become neutral, and the positive has become neutral. And once they both have the same charge, no more charge can flow because the potential difference. Here's another example that happens much quicker. It's a smaller capacitor. The light bulb lights up but very quickly goes out as soon as the potential difference is equal. So again, all that was meaning to illustrate is that this flow stops, right? So this is cool that we can get the electricity to flow through a light bulb, but the only problem is I can't light up that light bulb for a long time. What we need is to somehow get electrons that were deposited on the positive side. I need to get them back over to the negative side. So to keep a current flowing, this says, we need a charge pump to bring electrons from the positive side back around to that negative side. And I use the word pump because the electrons do not spontaneously go that direction. The electrons don't automatically want to concentrate themselves. They spontaneously move from negative to positive. They do not spontaneously go from positive to negative. And the reason for that is the electrostatic force, because opposite charges attract, negative is attracted to the positive. But like charges repel. So the negatives do not want to be concentrated with each other. All right, so let's talk about charge pumps. Another word for a charge pump is just a battery. Actually, there's a lot of things that pump charge, that pump electrons against their natural flow back to the negative side, and one is a battery. A battery is a device that converts chemical energy to electrical energy. I'm going to tell you a lot about a battery in just a minute. Up till now, you may have thought that a battery is just a black box that magically powers stuff. Well, now you're going to know how that works. Another charge pump is a solar cell. A solar cell is a device that converts light energy to electrical energy. You got solar cells on a calculator. Some people power their houses. They have solar cells, solar panels on their houses. That's another form of a charge pump. A generator is another form of a charge pump. And a generator in general converts kinetic energy to electrical energy using water power, gasoline power. You might have a propane generator. Steam power generates electricity. Wind, all of these things with a hand crate and flashlight, same thing. All of those things are designed to rotate a device to take that kinetic energy of rotation and convert it into electrical energy. And there's a process there that happens that we won't go into. It's called electromagnetic induction. You don't need to know that, but that's what a generator does. All of these devices take electrons from that negative side and bring them back around to the positive side, or to the negative, sorry. They take electrons from the positive and bring them back around to the negative so that we keep the negative side negative, keep the positive side positive. So what we're going to talk about for a lot of the rest of this time is a battery right here. And that's what the next video is going to be about. So we're going to be talking about batteries.